Welcome back, ladies and gentlemen. We're going to be continuing our discussion of atoms and elements and the periodic table. The periodic table, as you've seen before, it's a thing that we've made. It's a constructed device. It's a tool. It doesn't have to be this way. We designed it to be this way on purpose because it means that we can get answers from it. We can find patterns in it and we can solve problems. I mentioned in the last video that this green piece of paper that you have is basically the answer key for this entire course, or at least this unit. If you learn how to read this properly, everything is here. If you learn how to read this properly, right? If you learn how to use a hammer, you can build anything. If you learn how to drive a car, you can get anywhere. If you don't, you're just going to hit your thumb or you're going to crash somewhere. So you got to make sure that you understand how this works. But what are we going to be looking at? Well, first of all, this particular table was invented by a chap called Dmitry Mendeleev. He was a Russian guy. He managed to do two big things. One, he invented the periodic table. And two, he figured out a better way to make vodka. He made a lot of money. What can we say? So the periodic table, he came up with this basically by realizing that there was something wrong with the information he already had. Originally, when people were studying the elements, they would study each and every individual element separately, and they couldn't really see there was any connection to them. But over time, people got more and more and more information, and as they collected more information, they started to combine it together. And he, Mendeleev, managed to start realizing that there was a pattern to it all. A pattern that only worked if he left gaps in the numbers that he had, empty, blank spaces in the table. And that told him that there were elements out there that he hadn't discovered yet, that no one had discovered yet. And the weird part was that he managed to get it right. This table started off very empty. Heck, when I was your age, the whole bottom row was basically missing. But over the years, we have managed to slowly add one element at a time, making the table bigger and bigger with a better understanding. Now, in theory, that means that the table I had to memorize as a student is smaller than the table you have to memorize as a student. So on the plus side, I'm not going to ask you to memorize it. Well, okay, maybe the first 30. First 30 are pretty good. If you memorize the first 30, it'll make you have to do a lot less work going forward in this particular course. But here's the thing. You don't actually have to memorize everything. You just need to memorize the right things, and everything else will fall into place. What do I mean? Well, let's take this down and take a closer look at it. As I mentioned last time, the periodic table has a particular shape to it, a particular structure, right? This shape, this structure is designed this way on purpose. Understanding this shape will allow you to accomplish amazing things. First thing, the periodic table goes up numerically by atomic number, the number of protons. So we have 1 up here, 2 on the far side, and then 3 here, and 4, 5, 6, 7, 8, 9, 10. And then 11, of course, is over here. So the first part about this whole thing that tends to be a little confusing is that the periodic table isn't actually flat. It's actually a cylinder that looks like this. The two sides connect together and it spins and rotates around. So that way, of course, as should be logical, 2 and 3 are next to each other, as is 10 and 11, 18 and 19, 38 and 37, 36 and 37. I don't think it should surprise you that this table goes all the way around. So why is it flat? Because this fits in a book. I can't take a cylinder and stuff that in my bag, not easily, but this, flattened out, does. So that's the first major surprise. This is actually not a flat table, it's a cylinder. The other thing that's of interest here is what we talked about last time, orbitals. We talked about how hydrogen and helium have one orbital, right? We drew that out, and we saw that hydrogen had 1 electron in the outer shell. Helium had 2 electrons in the outer shell. Then we saw that there was good old lithium, which has 3 electrons in total, 2 in the inner shell and 1 in the valence shell, the outermost shell. This pattern continues even up to fluorine that we talked about last time. Will have 2 electrons in the inner shell, and it will have 7 electrons in the valence shell. Why so many? Well, because fluorine needs 9 electrons in total, and they can only fit 2 in the center, and then 8, and then 8. I mentioned this a little bit last time, but now we're going to take a look at it in more detail. Every row on this periodic table, every row adds 1 more shell. I have 1 shell here. I have 2 shells here. 3, 4, 5, 6, 7. 7 shells. Don't worry about these guys at the bottom. 7 different shells. Each time I go down 1 row, I add an extra valence. That's very convenient, isn't it? So why does the periodic table have this particular shape? Because every time they got to the end of a shell, every time the shell was filled, they started a new row. That's actually what periodic means in the name periodic table. A table is just a chart that you can pull out and look at. Periodic is a fancy way to say repeating pattern. There is a repeating pattern to this table. Every time I fill a shell, I start a new row. Okay, that explains the rows. What about the columns? The columns have another name. We call them families. Why do we call them families? Because they're related to each other. They behave kind of similar. What does that mean? Well, let me show you. In the periodic table, hydrogen was our first element. Lithium is the third. If we look at our table, hydrogen is, of course, right there. Lithium is right underneath it. Let's take a look at the next guy on our list, sodium. Sodium is in the 3rd row, so it has 3 shells in total, right? 1, 2, 3 rows, 3 shells. All right, so let's start drawing this out. Sodium. We're going to have 1 shell with 2 electrons. Easy. Then we're going to have a second shell, which will have 8 electrons, because of course it will. What else could it have? Why do I know the second shell is filled? Well, because, as we discussed, we only add a new shell when we've already finished the old one. So these guys here are going to be full. Now, at this point, how many electrons do we have? Let's see. 8, 9, 10, right? Because we have 8 in the outside in the second shell and 2 in the interior shell. But if we take a look at our periodic table, we see that sodium is atomic number 11. If it's 11, that means I need 1 more electron. So I'm going to stick that here. Can you see the pattern? Don't worry about helium and fluorine here. We'll erase those. We don't need to worry about those at the moment. Can you see the pattern between these 3 elements? Obviously, they have things that are different, right? H, Li, Na, and very different on that. But they have some things in common, don't they? Not the number of electrons. No, no. No, those are different, right? 1, 3, 11. But they have the same number of electrons in the valence, the outside. There's 1 electron here. There is 1 electron here, and there is 1 electron there. Guess how many electrons potassium has in its valence? Potassium is the next one going down the list. It's number 19. It too has 1 electron. I just erased fluorine. Why did I erase fluorine? We need fluorine. Let's think this through. Is this pattern true forever? Fluorine has got 2 electrons in the inner shell, and then it has 1, 2, 3, 4, 5, 6, 7 electrons in the valence, right? Because it has 9 electrons in total. What's underneath fluorine on the periodic table? If we go down the family, down the column, what do we see? We should see chlorine, which has 2 electrons in the first shell, just like everybody else. Then it has 8 electrons in the next shell, because that's the most it can hold. And that brings us up to 10. But chlorine has more electrons than 10. We check our table and we see that chlorine is up to 17. We need to put 7 more on here. 7 more on here. We pair them up, of course. 1, 2, 3, 4, 5, 6, 7. Connect the dots. And take a look. 7 on the valence, 7 on the valence. So this family, much like, say, my family, would be noted by having a lot of brown hair. Well, when there is any. A lot of brown hair for my family. Your family might have blonde, or it might have red. You might have blue eyes or brown eyes. This family has 7 valence electrons. This family has 1 valence electron. Why is this important? I mentioned last time, but a lot of chemistry happens with the valence. To be honest, to the point where the inner shells, right, the second and first one here, the first one here, second and first one, the inner shells barely do anything at all. The valence shells do everything, absolutely everything. So they're so important that we organize the elements into the families to show which shells or which elements had the same number of electrons in the valence. So every single element in the first column has 1 valence electron. The second column all has 2. The third column over here, yeah, there's a big gap. We'll talk about these guys later. The third column has 3 valence electrons. Fourth, fifth, sixth, I'm almost going in straight lines, 7, and of course, 8. The 8 columns each have the same number of electrons as they do their position. And you'll notice, if you look at your periodic table, that they're even labeled that way. 1, 2, 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. Now the B part, again, down here in the middle, we'll talk about them later, don't worry about it. Things get more complicated later, it's always the case. But why is this important? Well, because of the way chemistry works, all of these particular elements in these families basically behave the same. If you understand how hydrogen works, you basically understand lithium, sodium, potassium, and all the rest. If you understand fluorine, you understand chlorine. So you don't have to memorize all 118 elements. Wow, there's already 118. You don't have to memorize all 118. You have to memorize 8. The first element in each family. And then everyone else underneath behaves the same way. That's always beneficial, right? You get to not do as much work, but you get all the same information. Patterns are like that. If you can find patterns in what you're doing, you will save yourself loads of work. So I'm going to now spend some time. We're going to fill in our periodic table and see if we can't map out all these different patterns. Because as I said, the periodic table that you have, you get on tests, and it's basically an answer key for the whole test, if you know how to read it. So we'll do a quick sketch here of a periodic table. All right, so we're going to do, here we go, we got some hydrogen up there. We're going to go across like so. We're going to go up. Here's our helium. We're going to go over. We're going to come down. We're going to go down 2 rows, and we go across. That's almost the same on both sides. Fix it up. There we go. All right, here's our quick periodic table. And you know what? We've done too much black. Let's get a few other colors in here. All right, we got 4 other colors. Let's get some information. Okay, first things first. We already said, every time you go down a row, add 1 orbital. Every time you go down a row, you add an orbital. Okay, that's step 1. Step 2, every time you go to the right, you add 1 valence electron. Every step you go to the right, you're going to add 1 more valence electron. What else are we going to do with that? Well, we got to make sure we understand. Each family shares properties. So if you know what the first one does, you know what all of them do. So it's important for us to know what the different elements are. All right, well, let's write them down. We need those first ones. They're going to be important. Our very first one up here is hydrogen. Okay, hydrogen is going to be pretty insignificant. Then we're going to have ourselves some beryllium down here. Then we're going to have some boron, then carbon, then nitrogen, then oxygen, then fluorine, and then helium. Okay? If you remember those guys, just whatever each one of them does, all the rest of them do the same thing. Now, because of that, we actually name the families. The families have names because it's a little easier to remember than just like the hydrogen group, give or take. So the name for the first one here, it's a little bit of a weird one. I mean, the first 2 are probably the weirdest, and then they get pretty simple. The very first one is called the alkali metals. The alkali metals, you probably remember that from grade 9. So this one here is going to be the alkali metals. Next, you've got the alkaline earths. Then we jump way over here, and this one here, it does actually have a super fancy name, but we're just going to call it the boron family, because the super fancy name is the triols family. I believe that's how you pronounce that. Nobody uses that name anymore. It's too old. The next one we just call the carbon family. It also has a fancy name. That would be the tetrals family. Tet meaning 4 in this case, so the 4 family. We'll see why they're 4 later. The next one is called the nitrogen family, or the pnictogen family, because they've got nitrogen in it. We're just going to go with nitrogen family. Oxygen is next, which can be called the chalcogen family, because originally oxygen had the name chalcogen, sort of. That's not quite right, but the thing that was the precursor, what led to oxygen, was called a chalcogen. But we're just going to call it the oxygen family. Okay, now the next one you'd assume is the fluorine family, given the pattern we've been following, but no, this name is actually used on a regular basis. This one is called the halogen family. And then we've got one last one. And again, you'd think, okay, fine. Is it the helium family? It's not the helium family. It could be, but no. We call this the noble gases. The noble gases. I remember I asked my grade 9 students a question, and I said, quick, the noble gases, are they solid, liquid, or gas? And they all went, I don't know. The noble gases are generally gas, not all of them, but most of them, and they're called noble because they don't really do anything. Like at all. We've basically found only 2 things that we can use them for. One, fluorescent lights. If you run electricity through a noble gas, it'll glow. Turns out we figured that out. That only took until like the 1960s. 2, insulation. You can put things like argon between panes, between sheets of glass in a window. Right? You fill the space with with argon, and it helps to stop the heat from escaping from your house, right? That's why most houses in Winnipeg, for example, we've got many, many layers of glass. We'll have like 2, 3, 4 layers of glass in order to stop the heat from escaping because it's really cold outside. So there we go. We've got our families, and remember, each family shares properties. So whatever the first guy on the list does, the last guy on the list does pretty much the same thing, but, a little bit different. And as you move to the right, you add one valence electron. And of course, as you drop down, you add one orbital. The other thing we can see, doing green, the maximum electrons, max electrons equals the number of elements in a row. Let's say max electrons in a shell. Actually, hold on here. Do it in blue. Keep it with the same color scheme. So the max electrons in a shell equals the number of elements in a row. So the first row has only 2 elements in it, right? Hydrogen and helium. There's helium. So there's a maximum of 2 electrons in that shell. The second row has a total of 8, so there's a maximum of 8 electrons in that shell. The next row is also 8, so it's 8. The row after that is 18. We'll get to them later. Okay? Any questions so far? Hopefully not, but if so, send me a message. Ask me. We'll talk about it. All right? Trying to see. Is there any other things that I normally try to talk about or mention? There's one more thing, but we'll get to this when we talk to ions. But you know what? We'll toss it on the page, right? We'll mention it here just as a small little side note. Every element wants a full valence. That'll make more sense when we get to ions. But for now, you can write that down, and we'll see what we mean by that later. Now, we've mapped out our periodic table and its general behaviors and certain patterns that we can use, and I told you that you only need to memorize the first element of every family, and once you know that, you know what all of them are going to do, so it would be really good if we knew what each one of those did, right? Let's take a look at the alkali metals first. First things first, most reactive metals are on this particular family here. These are very reactive, which means that they're some of the most common elements in the universe because they're so light, right? Hydrogen, tons of it everywhere. It's the most common element in the entire universe, but it's pretty rare on Earth. Yes, I know water is made of H2O, the H's are hydrogen, and yes, there's a lot of water on Earth, but there's a lot of hydrogen in space. Like, there's a lot of water on Earth, but I'm currently not underwater, and neither are you, probably, which means that there's parts of the Earth that aren't water. Well, most of space that has matter in it is hydrogen, and like that's it. So hydrogen is the most common element. On Earth, alkali metals are always found combined with other things to make more complicated materials. The simple reason for this is because they're so reactive, meaning that they don't really want to be alone. They want to fill their valence, whatever that might mean. We'll figure that out later. But what that means is that these guys over here, the alkaline metals, there we go, these guys are hard to get a hold of. Like if I want to dig them out of the ground, I'm going to be digging up a lot of rock, and then I'm going to do some chemistry to split them apart. So one cool feature about all of those guys, they burn on contact with water. I've got a couple extra videos in the plan that you should watch. One of them talks about the periodic table and Dmitry Mendeleev's ability to create the table. The other one shows you things burning in water. So that's always pretty cool. Next one, we got the alkaline earth metals. Now, the earth metals are basically the same as the alkali metals. The earths, though, are more, or I should say, are less reactive. So like if lithium, so let's go with sodium. If sodium bursts into flames in water, the one next to it, magnesium, It doesn't, right? So sodium is right here. If it burns on contact with water, magnesium kind of smokes, at least until you light it on fire. Magnesium may be a bad example. Magnesium actually does burn underwater. It's quite cool. All right, then we jump across the gap here and we get to the boron family way over here. Now, I wonder why there's a reason. Is there like a reason why there's this huge gap between those two? There totally is. One thing at a time, though. Boron family. What's the boron family going to do? It's basically the less reactive version of the other two. So we're sort of like stepping down in terms of reactivity, right? We started with the highest, and then we went lower and lower. You'd think that the next family, carbon, is going to be even lower, but wait, spoiler alert, things are going to change a bit. So the boron family is a weird one because it's sort of this boundary between the left and the right sides of the table, right? The left sides of the table behave a certain way and the right side behaves a certain way. That's why there's this gap in here. But we'll get to that. We'll get to that. Next, we're going to take a look at the carbon family, okay? It's the most flexible family. It can do the most things, right? And as a result of that, it is the fundamental building block of all living things and cell phones and electronics. All electronics are built off of silicon, which is directly underneath carbon on our list here. Carbon, of course, is what you're built off of. So you and your cell phone are sort of built off the same thing. Not really. Your cell phone isn't totally alive. It just seems that way sometimes, especially when it does that phantom buzz. Bzz. Anyway, the study of carbon is so important. The carbon family is so important that it's got its own branch of chemistry called organic chemistry. Organic just means carbon. All right, all right. Next one, nitrogen family. What's so special about them? Not a lot. They're kind of the slightly less reactive than the guys to their right. So it sort of goes like most reactive, less reactive, less reactive, most flexible, not necessarily most reactive, but most flexible. Then we're going less reactive, more reactive, more reactive, not reactive at all. What? That seems kind of a weird pattern, doesn't it? It's like we're going from high to lower to lower to sort of flat or middle. I don't know. It's sort of weird. And then it goes like, starts off here, and then it goes up, and then up again, and then it goes to zero. Not every pattern is easy. So the nitrogen family, the nitrogen family, these guys here, they don't do a ton. You know, nitrogen's in the air. You breathe it in all the time. It's nitrogen. Doesn't do much. Oxygen. That one you know that one. That one causes fire and living. You need to breathe that in order to live, right? You burn food by breathing in oxygen. You've got like a little fire inside of you. But it also causes fire and explosions and missiles and bombs and fireworks and all these cool, awesome things that burn. They're pretty useful stuff. But remember what I just told you. We're stepping down. We go from most reactive to less, and then this guy here is the least reactive on the right side of the table, slightly more reactive than the N's. The F's, the halogens, those are the most reactive of these three. Which means that fluorine, like oxygen is the thing that causes fire and explosions. Fluorine makes oxygen look like it's taking a break. Fluorine is so nasty that chemists generally don't want to touch it because it's too dangerous. No, you can't have fluorine. Don't even have. Nope. No, I know you wanted some, but you can't have it. Yeah, I know what you want. So, in their natural state, these guys are so reactive, you never find them by themselves. They're always combined with something else, much like the guys on the other side of the table. It's almost like the two extreme versions here are kind of similar in some way, and then these two are kind of similar, and then these two are kind of similar. It's like there's a pattern of some form. Finally, we got our noble gases, right? Guys, at the end here, the noble gases, of course, they don't do anything. They are inert, meaning they do not react in any way. That's it. They don't react in any way. All elements want a full valence. Valence. These guys already have it. So they're already happy. They got all the money they need. They've got their recent game console. They've got all the food they want. They are set, and they just chill. So there's one more thing for us to kind of talk about. Because I kept mentioning that there's this dividing line between the left and the right of the periodic table. What could that be? The left of the table tends to have certain elements that you might recognize. Not necessarily in the first few columns, right? Maybe you recognize calcium, right? Strong bones. But in this middle area here, there's ones like iron and copper and tin. Tin should be over here, I think. And gold and silver. No, silver than gold. And those are all metals. Metals. And we use that. We will look at the table and we will divide the table into two sections. There is the section over on this side, which we call the metals. And then there's the section over here, which boron is the dividing line. And that section we call the non-metals. Because naming is hard, and chemists are bad at it. So we've got option 1 and option not 1. They could have called it option 2, but nope, they decided to call it the same thing, but not. So the metals all behave in similar ways, as we're going to see when we go forward with this. The non-metals will all behave in similar ways, as we're going to see when we go forward with this. That's kind of why there is this division. Now, this little staircase kind of thing that I just drew, that's the dividing line between the metals and the non-metals. Everything on the left of that line is the metals. Everything on the right is the non-metals. You don't need to absolutely memorize that. Just kind of know that boron is the one that sort of marks the boundary, and then it sort of drops off below that. Directly below boron, right here, would be aluminum, which by any stretch of the imagination is quite metallic in nature. So, what does this all mean when we put it all together? Well, the periodic table has a series of patterns that we can make use of. We increase the number of valence electrons as we go right. We increase the number of shells as we go down. We know the maximum number of electrons that can fit in a shell by how many possible spots there are on the table. There's 2 in the top row, there's 8 in the next 2 rows, 18 in the next couple rows. It makes it pretty easy. You just got to count. Counting, something I hope you can all do. We also understand that these guys all have families, and everybody in a family behaves the same way. But we can also divide this even further, and we can say that there are metals and there are non-metals. And these two big categories split the table kind of in half. To be honest, most of them are metals. There are very few non-metals. But what do we know about these guys is that the metals and the non-metals behave differently. This whole situation with metal, non-metal, it's called a binary choice, meaning 2. Bi means 2. A binary choice, which means that everything that this guy has, this guy doesn't have. Binary choices are very convenient, like left and right, yes and no, up and down. Because whatever one is, the other one's the opposite. So take a moment, think about it. What are some properties of metals? What do you know about metals? Like, are they usually solid, liquid, or gas? Are they shiny? Are they dull looking? Can you conduct electricity through metals? Can you bend metals and work them with tools to make them into shapes? Well, the answer to almost all of these is yes. Metals are solid for the most part. They're shiny, right? That's the whole reason why metal works the way it does. Metals are workable. I could take tools and shape it into a different thing. I mean, this is shaped into the shape of a key, right? It didn't come out of the ground this way. We shaped it this way. And do they conduct electricity? Oh, most certainly. When you were a little kid, you probably tried to take a key and stick it in a light socket at one point because you saw your parents do the same thing in their car. You probably got a shock from that if you gave it a shot. Or perhaps you were stopped at the last minute, and now you want to do it because I mentioned that you could. But all of these, of course, conduct. So now let's think about our non-metals on the other side. Well, non-metals. This part of the key is non-metal. This part right here. It's plastic. Plastic isn't metal. Plastic is actually made of carbon. Well, is it solid? Yeah, actually. But not all of them, right? These guys here are all gases. There's also a couple liquids in here as well. Well, a couple. But some of them can be solid, so it's a mix. Is it shiny? No, not by any stretch of the imagination. Look at that. It's quite dull. If I hit it just right, but I mean, look at the difference, right? The key is glaring like crazy, and this is barely shiny. Is it a good conductor? Not in the slightest. That's why we put rubber around wires. We put nonmetals around wires to protect ourselves. Is it malleable? Can I easily shape it? No. I can pour it sometimes, but often they're not very cooperative. I can't really make a wire of nonmetal. It doesn't work. And even if it did, it would be a poor conductor. So what would I do with it? So these two are binary choices, and they kind of just do the opposite of each other. Of course, there is that whole boundary area, right? The line itself. What do the guys on the line do? Well, the guys on the line are called metalloids or semi-metals. They're half non-metals and half metals because they're half and half in terms of where they are. They tend to be solid. Good. They tend to be shiny. Awesome. Sometimes they're good conductors of electricity. Sometimes. Mostly they're not. They're called semiconductors. Very important for electronics like your cell phone and the device you are currently watching this on. And they're not very malleable. It's hard for me to shape them into a particular form. I can, however, break them really easily. They're brittle. They snap, most simply. And you can see this, all of these properties, by me just pulling out some examples. I have a pencil here. It's made of non-metal. If I take that pencil and apply pressure, I'll snap it. It's not going to move except to break. However, if I reach over here and pull out a paper clip made of nice aluminum, I can take it and I can bend it because the paper clip is malleable. So this paper clip is clearly a metal, whereas the pencil is clearly non-metal because it is brittle. A metalloid, a semi-metal, the boundary line halfway between the two worlds, would be brittle as well. And I'm not going to demonstrate that by snapping my cell phone. Sorry, guys. I leave that as an exercise to the viewer. I don't recommend it, but I leave it to you. Anyway, that's it. That's the entire periodic table. Well, almost. There's one last piece. But that is going to require us to have a better understanding of ions. And that'll be next time. So I'll see you guys then.